For the function below, we want to find the critical numbers and open intervals of increasing and decreasing behavior. So the function that has been given to us is f of x is equal to x plus 6 raised to the 6/7th power. The first thing that we have to notice is that critical numbers are being found by first finding the derivative of my original function and then investigating the zeros of my derivative and possibly values where the derivative is undefined. Now, critical numbers are those ones that are still in the domain of the original function of this. Now, there is nothing really bad happening with this function right here. There are no values for which this function is undefined, so every value that we are going to find will be considered a critical value. So let's go ahead and find the derivative. First, find the derivative of x. What happened to my tick mark? The derivative of f. In order to find the derivative of f of x, we're going to have to use the chain rule, which states that we have to use the derivative of the outside multiplied by the derivative of the inside. And we are using for the outside derivative our power rule, x plus 6, 6/7 times x plus 6 raised to the 6/7 minus 1, or in other words, minus 7/7. So we are getting that the derivative is 6/7 multiplied by x plus 6 raised to the -7. I would really like to write this in the following way. With a positive exponent raised to the +1/7 is nothing else but the 7th root of x plus 6. Now what we are going to have to do in order to find the critical numbers, we are going to set this derivative now equal to 0. Second, set the derivative equal to 0. That means we have 6 divided by 7 times the 7th root of x plus 6 is equal to 0. We can multiply by the reciprocal of 6/7, and we are getting something a little bit simpler looking. The 7th root of x plus 6 is equal to 0. Now, this expression on the left side can never be 0, because then we would have division by 0. But it is undefined. Undefined when x is equal to -6. X cannot be -6 in this case. That means -6 is a critical number because also f of 6, my original function, is still defined at -6. It is 0 at -6. So for A, the critical number is -6. There is only one. Now to the second part of this question. We want to find out where the function is increasing and decreasing. Now, if I would have a graphing calculator, this would be now a very easy task for us. I would just type in, I would display the graph of the function. I could visually see where my function goes down and where my function is going up, from left to right. This is one more reason why we do not want you to use graphing calculators. So I want to remind myself of a simple fact real quick. This is a trick that is going to come in handy also in the next few sections when we are looking at concavity of a graph. So I am always starting with a very simple graph, the graph of my quadratic function f of x is equal to x squared. Now the derivative of this function is just as easy to sketch. This would be the function f of x is equal to 2x. Now the reason why I'm sketching both of these graphs in the same coordinate system is because now I can visually see what is happening. When my first derivative is positive, my original function was increasing. Where my second derivative is negative, my first derivative is negative, my original graph was decreasing. And where is it switching from increasing to decreasing? Well, exactly where my first derivative was crossing the x-axis, where it was 0. So these are possible points where my function is changing its behavior. Possible. So in order for me now to find out where the graph of this function is increasing and decreasing, of my original one, I am just going to have to pick a value to the left of -6 and to the right of -6. Substitute these values into my derivative and see whether these numbers will spit out negative values or positive values. So the easiest numbers I want to argue to use in this case would be to the left of -6. Let's use -7. For B and C, use test values. All right, let's start with the first one. And remember, you have to plug it into your derivative. To the left of -6, -7. I'm gaining now 6 divided by 7 times the 7th root of -7 plus 6. What are we going to get out of this? -7 plus 6, this would be -1. And we have 7 times the 7th root of -1, which is -6/7. This value is less than 0, which is all that we needed. So, f is, what is it doing? Smaller than 0. My original function was decreasing. F is decreasing on the interval from -infinity all the way up to +6, because we picked a value out of this interval and plugged it into the first derivative. Now let's do the same thing with a number to the right of -6. In other words, I am now going to look at the interval from -6 to +infinity. We are to the right. Let's use -5. I have my derivative. I plug in -5. -5 plus 6. The 7th root out of this is nothing else but 7 times the 7th root out of +1, which is +6/7. And that is greater than 0. So f is increasing on the open interval from 6 all the way up to +infinity. Let's have a look which one is the answer for A and which one is the answer for B. For B, they wanted to find where the function is increasing. So we have found out this is the answer for B. And right here, is our answer for C, where my function is decreasing.